Welcome to Unit 2. Today we're going to start basic chemistry. We'll do the first 42 slides this week and the next 42 slides the following week. So it's nice to split these chapters up. They can be pretty lengthy, especially the first few, the basic chemistry one, the cellular one. They can be a kind of lengthy chapter. So we're going to split those up between weeks. So this week we're going to start off with a case study. This is Maureen and her baby Sean. Sean is Maureen's first baby. Maureen and her husband Connor had enjoyed an uncomplicated pregnancy and delivery. Maureen had felt healthy throughout the pregnancy, but something was wrong with her baby. He's 1 month old and not thriving. He seems to have a good appetite and breastfeeds as if he were starving, yet he has dropped 20% of his normal birth weight of 7 pounds 8 ounces. He's down to only 6 pounds at his 1 month checkup, and his skin looks wrinkly. His stools appear greasy and foamy, and Maureen also notices that Sean's skin tastes salty. Most alarmingly, he seems to be having some difficulty breathing. His breathing is wheezy. Maureen and Connor are both from big families, and none of the babies in the family has ever been sickly like this. So, throughout the course of this lecture, we're going to figure out what's wrong with baby Sean. We'll talk about it more next week once we've gone through the whole chapter, but just keep it in mind as we go forward. So, an introduction to chemistry. Chemistry is a science that deals with the structure of matter. Matter is anything that takes up space and has mass. It determines an object's weight and is not technically the same thing, but for the purposes of this class, we can say that mass and weight are basically synonymous. Everything living and non-living is made of matter. You're made of matter. The air is made of matter. The desk you're sitting at is made of matter. Everything. The smallest units are called atoms. So the very smallest units that make up you or anything else is an atom, which are composed of subatomic particles. So sub meaning below. So below the level of atoms there are these subatomic particles. There are protons, neutrons, and electrons. Protons have a positive charge, neutrons have a neutral charge, and electrons have a negative charge. And that will be really important as we move forward. So what do these atoms look like? Generally, they have a nucleus where those protons and neutrons kind of sit, and then the electrons form an electron cloud surrounding that nucleus. The electron cloud can be seen in a 3D model, or if you have an electron microscope and you're looking at these atoms, you can see them in kind of a cloud formation surrounding the nucleus. When we think about this conceptually or in a 2D model, we think of the electrons in more of a shell format. So we'll talk about that as we go forward too. Typically, the number of protons that are found within an element or an atom are equal to the number of electrons that are within said atom, meaning that that element is electrically neutral. The atomic number is the number of protons that are found within an element or an atom. So an element is really just a substance that's made of all of the same atoms. So for example, neon is an element. It's made up of many atoms of neon. When you look at the periodic table of elements, the elements are ordered based upon their atomic number. And generally each column is going to have similar chemical properties. So if we look at neon, neon is an element of neon atoms, right? So its atomic number is going to be either in the left-hand or right-hand corner, typically on a periodic table. So neon has 10 protons, and because protons and electrons are usually the same, neon also has 10 electrons. When in this cloud formation surrounding the nucleus, these electrons move extremely quickly. They're constantly colliding with each other. The more quickly they move and are reactive with others, the more unstable the element is. So like I said, elements are pure substances with atoms of one kind. So with neon, neon is made up of a bunch of neon atoms. Carbon is made up of a bunch of carbon atoms. So the difference is just how many protons, how many neutrons, how many electrons there are that distinguish these elements from each other. Overall, there are 92 that exist in nature. 24 are also included on the periodic table that have been man-made. Each element is going to have its own chemical symbol. For example, sodium is Na. Na stands for natrium, which is the Latin name for sodium. Most of the chemical symbols are based upon the Latin names of the element. Elements can also not be changed or broken down. They are the smallest they possibly can be as an atomic structure. In the human body, these are the elements that are most commonly seen. We have oxygen, carbon, hydrogen, nitrogen, and the list goes on. You can read through these, and they have a lot of significance in the functions that they perform in our bodies. Isotopes are going to be elements that have atoms that have the same proton number, but they have different neutron numbers. So because they have different neutron numbers, they'll have a different mass number. So if we go back and look at neon, neon's mass number is located here at the bottom below its name. So its mass is 20. The mass number is the number of protons and neutrons combined. If this were an isotope of neon, we would be able to tell because the mass number would not be 20. So this is standard for all neon. Isotopes are going to have different mass numbers. I definitely don't expect you to memorize atomic numbers, mass numbers, or anything like that. You will always be able to see a table of elements which has all of these numbers included. So another example of isotopes you can see here on the bottom. Hydrogen is element number 1. Hydrogen by itself has no neutrons. It only has a proton and an electron. But an isotope of hydrogen is deuterium. It can also be abbreviated hydrogen 2. Hydrogen 3 is tritium because it contains 2 neutrons, and so on. So the isotopes may have different names than the original element, or they may just be the element named with a number either before it or after it. Typically, isotopes have the same chemical properties as the original element. Sometimes they differ if they are radioisotopes. So radioisotopes tend to be very unstable. They break down and they release radiation when they undergo radioactive decay. So the decay rate is also known as the half-life. So the half-life is the amount of time it takes for half of the isotope to decay. Chemists, radiologists, they use this a lot in nuclear medicine. Radioisotopes are used all the time in diagnostic medicine. So if you've ever had a CAT scan or an MRI where you needed contrast, you had a radioisotope injected into you so that they can further see different structures in your body. Of course, those are very weak radioisotopes, radioisotopes that are stronger or at high levels can be really dangerous and cause radiation poisoning. So the atomic mass is different from the mass number. So remember, the mass number is the number that's located at the bottom of the element, typically underneath the chemical symbol or the name. The atomic mass is going to take into account different weights of atomic particles. So average out all of the atomic masses, the mass numbers, and all of the proportion of isotopes that exist. Generally, this is notated in moles, and moles are specific quantities for elements because they're so small and they weigh so little. So it's like grams or pounds, but extremely, extremely small. So let's talk a little bit about electrons. So remember, in a 3D format, if we're looking at them in nature in an electron microscope, they occupy electron clouds surrounding a nucleus. If we're looking at a 2D model, they're occupying energy levels within shells. So the rule of thumb with energy shells, or electron levels within shells, is that the first level is closest to the nucleus. It's the lowest energy shell. It's the lowest energy level, and it contains 2 electrons, maximum. Any energy level following the first energy level is going to contain maximum 8 electrons. This will all depend on how many electrons that the element typically carries. So for example, hydrogen has 1 electron, so therefore in its energy level, it would only have 1 electron in the inner shell and no other shells would be filled. Another example would be helium, which is our next element. It has 2 electrons. So its inner energy level would be filled because it has 2 electrons that would fill it, but no other electron levels would be filled. We'll look at some other examples as we go forward. The octet rule states that in the outermost energy level, which is known as the valence shell, if it is filled with 8 electrons, then that is the most stable that the element can be. Any unfilled outer shells will lead to that atom or element being unstable. If they're unstable, they're more reactive and they're more likely to form chemical bonds with others to stabilize themselves further. So let's look at an example here. So hydrogen, like I said, has 1 electron, so it only has 1 electron in its inner shell. So hydrogen is going to want to bond with other things to make it less unstable. Helium has 2 electrons on its inner shell, so its inner energy level is filled. Lithium is our next element, so its atomic number is 3, so that means that there's 3 protons, and since protons and electrons are typically the same, that means it has 3 electrons. So its inner shell will be filled with 2 electrons, and its outer shell will start to fill, but it only has 1 electron, so lithium is very unstable. And then we have our original example of neon. So neon, its atomic number is 10, so that means it has 10 protons. Therefore, it has 10 electrons. So you have 2 electrons that fill the inner shell, and the outer shell is filled with 8 electrons. So its valence shell is filled, meaning it's inert, stable, and unreactive. So neon won't want to form bonds with others. It will be stable by itself. So speaking of being inert, neon is one of the noble gases, meaning it's inert, it has a filled valence shell, and it has no active chemical properties. There are no chemical reactions that it undergoes. So this is an example of the columns of the periodic table typically having the same kind of chemical properties. Here on the very right-hand side are all the noble gases here in pink. So all of the noble gases are inert, they have no active chemical properties, and all of their valence shells are filled. So we're going to start talking about chemical bonds. Although noble gases aren't going to want to form bonds with others, you can see that if you don't have a filled valence shell, the best thing to do is to form a chemical bond to gain some stability. So any of the other elements are known as reactive elements. They interact and they combine with other elements to become more stable. Molecules are going to be any elements that combine to share electrons. Compounds are going to have two or more different elements, and the electrons there are not necessarily shared. They can be, but not always. Compounds are going to have extremely different chemical properties than elements, especially since there's going to be a mix of elements. So, an example, an oxygen molecule is going to be two oxygens bonded together. They're going to share electrons in order to fill their valence shells. An example of a compound is sodium chloride, NaCl. They're not going to share electrons, but one donates an electron to the other. Sodium chloride is known as your typical table salt that you might use while you're cooking. So we said that molecules are going to share electrons. So molecular weight of something is the sum of the atomic weights of the atoms that are combining to form this molecule. So in a hydrogen molecule, it would be two hydrogens coming together and the mass of those two hydrogen atoms. Another example is a water molecule. So a water molecule is composed of two hydrogens and one oxygen. So to figure out the molecular weight of water, you would combine the weights of two hydrogens and an oxygen. That is why it's abbreviated H2O, because there's two H's and one O. Ionic bonds. So these are one of our first types of bonds. They're the second strongest bond that we're going to talk about. Ions can be split into either cations or anions. For something to be an ion to begin with, it means that it has an unfilled valence shell. If you're a cation, you've lost an electron. So that makes the element slightly positive. Because if you remember, electrons carry a negative charge. So if they lose an electron, they become slightly more positive than they were before. Anions have gained an electron. So they become slightly more negative because electrons are negative in nature. So if they have an extra electron, they'll be slightly more negative than they were before. So let's look at this example. Naturally, or in nature, sodium has 11 electrons. Chlorine has 17. So you can see that if sodium just got rid of this extra electron, then its outer shell would be filled with 8 electrons. And if chlorine could just gain an extra electron, its outer shell would be filled with 8 electrons. So typically, sodium and chlorine form a bond. So first, sodium donates that electron to chloride, making sodium slightly more positive, so it would be a cation because it lost an electron. And chlorine gained an electron, so it became slightly more negative. Typically, anions are going to have the suffix "ide," so chlorine becomes chloride. And because they shared and lost an electron, they donated and accepted an electron, they formed an ionic compound or an ionic bond between these two elements to form sodium chloride. So that's table salt. So ionic bonds are created between attractions between cations and anions. They either donate or steal electrons, and many ions dissolve in water. Covalent bonds are the strongest type of bonds that we're going to talk about. They share electrons rather than donating and accepting. Covalent bonds can be single, double, or triple in nature. A single bond will be the sharing of 1 electron, double will be the sharing of 2, and triple will be the sharing of 3. Covalent bonds, just like ionic bonds, result in filled valence shells. Sometimes covalent bonds can form where the valence shells are not filled, and there are unpaired electrons in that valence shell, and that forms a free radical. So free radicals tend to be super reactive, they're destructive, they contribute a lot to the aging process, and they're even implicated in diseases like dementia and Alzheimer's. There are some really important free radicals that we have in our body, like nitric oxide, which helps to dilate, constrict our blood vessels. Covalent bonds can be either polar or nonpolar. Nonpolar covalent bonds means that the sharing of electrons is equal. Nonpolar covalent bonds are going to be found in a lot of the many different structural components of our bodies. Whereas polar covalent bonds are quite the opposite. They're going to involve the unequal sharing of electrons. An example of this is in water molecules. So in water molecules, the oxygen atom is more attracted to the electrons from the hydrogen atom than the hydrogen atom is attracted to the electrons that it carries. So because the oxygen kind of holds that electron from the hydrogen atom a little bit more closely than the hydrogen does, it creates this slightly positive charge on the hydrogen atom and a slightly negative charge on the oxygen atom. So there's no charge difference in nonpolar covalent bonds, but in polar covalent bonds there tends to be a bit of a difference. With hydrogen bonds, these don't actually make molecules, but they do create interactions between the slightly negative charge and the slightly positive charge that we spoke about before. In water molecules, we have hydrogen atoms from one water molecule attracted to the oxygen atoms of a different water molecule. Hydrogen bonding in water molecules allows for surface tension. So surface tension acts as a barrier for many lightweight objects. A good example of this is your mucous membranes creating a moist protective barrier around your eyes to protect you from dust. This is also how really lightweight insects can walk across water. And these hydrogen bonds tend to affect the shape of the molecules. They can create lattice-like structures. Okay, and states of matter. So I'm sure you guys have heard this in maybe elementary level science class, right? We've got solids, liquids, and gases. So solids keep their volume and their shape because their particles remain quite close to each other. Liquids have a constant volume, but they don't have a specific shape. They fill whatever shape that they're in of the container. And then gases are a constant volume, and again, they have no shape. And that's because their molecules tend to be way farther apart than that of something like a solid. Water is the only substance that exists in all three states of matter in life-compatible states. So at temperatures that can be compatible with life, water can be a solid, liquid, and a gas. No other element or molecule can do that. So we talked about different types of bonds, but we haven't talked about chemical reactions. So chemical reactions are the actual formation of these new chemical bonds or the breakdown of these existing bonds. So reactants are what are coming together to form products. You can think of this kind of like when you're cooking. Reactants can be the ingredients, and they come together to form the product of whatever you're making. Metabolism then, so you've heard if you have a fast or slow metabolism, that's all of the reactions in the cells and tissues in your body, whether that's maintaining your homeostasis, that's growth, that's maintenance of organs or tissues, anything that's happening in your body, your digestion, that's all contributing and known collectively as metabolism. So let's talk a little bit about energy. So work is going to be the movement of an object or the change of the structure of matter. Energy is your capacity to do work. So energy can be broken down into kinetic and potential energy. Kinetic energy is energy while you're moving, whereas potential energy is the energy where you have potential to be moving. So a quick example, throwing a ball. The actual throwing of the ball is kinetic energy because the ball is moving. Your arm is moving to throw said ball. If you were just holding the ball in your hands, not moving, it would have a lot of potential energy because you have the potential to move it, to throw it, to do work on the ball and with your body. Another example would be if you're on a ladder. So say your foot is on a ladder, you're about to climb it, but you haven't climbed anything yet. You'd have a lot of potential energy in your body. Kinetic energy is when you're actually starting to move. When you're actually starting to climb the ladder. One of the biggest properties of energy is that it cannot be destroyed. It can also not technically be created. It's only transferred. So any of the energy that's in the universe is just energy that's been transferred from one thing to another. A good example of this, if you think about it, you generate energy in your body based upon energy that you consume. So your body just takes all these molecules from the food that you're eating and transforms it into something that's usable for your body. You're not actually creating it, rather rearranging it so that it can be used. Another way that energy can be transferred is by releasing it as heat. So you can think about this if you're working out and you're starting to get really warm, your skin warms up, your body starts to warm up as your muscles are doing work. They're releasing some of that energy as heat. So some different types of chemical reactions, and we'll talk about each of these. Decomposition reactions, synthesis reactions, exchange reactions, and then any of those reactions can be reversible or irreversible. So decomposition reactions are your typical reactions that you see when you're digesting food. It's seen in a lot of other processes as well, but biologically and anatomically, we see this a lot with digestion. So it's the breakdown of a molecule into its smaller fragments. It can take place inside or outside of cells. If water is needed to break down this bigger molecule into smaller fragments, that's called a hydrolysis reaction. Collectively, all of the different types of decomposition reactions that are occurring in your body, breaking bigger molecules into smaller fragments, that's known as catabolism, and that's one of the main parts of metabolism. So metabolism is broken down into catabolism and anabolism, and we'll talk about that on the next slide. So synthesis reactions are the opposite of decomposition reactions. We're making large molecules from smaller molecules or smaller fragments. If water has to be removed in order to make these bigger molecules, that's called dehydration synthesis or condensation reactions. All of the synthesis reactions that are occurring in your body together are known as anabolism. So all of the reactions that are creating larger molecules and all of the reactions that are breaking down larger molecules are known as metabolism. Anabolism and catabolism together form metabolism. I know they all sound the same, but you can think of it as anabolism. There's a word that we know that is similar to that, like anabolic steroids. So you know that people take anabolic steroids when they're trying to bulk up their muscles, right? So we're making something bigger. With catabolism, think of like a catastrophe. We're taking something big and making it into small pieces. An exchange reaction is going to be exactly how it sounds. Parts of reacting molecules are going to be shuffled around to form new molecules. And as I said, any of those types of reactions can be reversible or irreversible. A lot of biological reactions are going to be freely reversible, and they will always tend toward equilibrium. So in equilibrium, there will be the same amount of reactants as there are products. So if we had 2 hydrogen atoms as reactants, we're going to want to have 2 hydrogen atoms as products somewhere within said product. So if we were combining 2 hydrogen atoms and 1 oxygen atom to form H2O, we still have 2 hydrogen atoms as a product and 1 oxygen atom as a product. So although they can be reversible, most biochemical reactions that occur in the human body are not spontaneous. If they were spontaneous, they would have absolutely no value to us. We need to be able to harness specific energies and processes to make our body functions possible. So in order for reactants to form these products, there has to be enough energy provided, called activation energy. Enzymes are needed to catalyze reactions. Catalyze meaning to speed up. So our body has tons of enzymes. Enzymes are a type of protein, We'll talk about that a lot next week when we do the second half of this lecture. Enzymes are a type of protein, one of the most important types of proteins in our body, and they help to speed up reactions. Most enzymes end in the suffix ase. So if you see ase at the end of a word, you're likely looking at an enzyme. An example is if you are lactose intolerant, it's because you have a deficiency in the enzyme lactase. Lactase breaks down lactose. Enzymes lower the activation energy of a reaction. So if you think about it, the activation energy acts as a kind of threshold. It's the energy needed in order to take those reactants and form them into products. So if that activation energy is lowered, that reaction can happen without the use of so much energy. Enzymes cannot be changed or consumed. They will always be present. They can denature, however. They have ideal conditions. So there are certain enzymes that like working at a specific temperature or pH in your body. There are some enzymes in your stomach that work at very, very acidic pHs, and if there are any pHs that are basic, they tend to not work as well. And enzymes only affect the rate of the reaction, not the reactants or the products. So enzymes are not going to change any of the reactants or the products. They're only going to speed up the reaction. As these reactions proceed toward completion from reactants to products, or if it's reversible from products to reactants, it can absorb or release heat. So in endergonic reactions, that chemical reaction is going to absorb energy. Exergonic reactions are going to release energy as heat. Exergonic reactions are a really good example of how you release heat when you're working out, like I said before. They help to maintain your body temperature. So we're leaning more toward now how these things can apply to your body, right? So in your body, you have nutrients, and these are going to be substances from the foods that you eat that are used for your normal functioning of your cells and your tissues and your organs. Those can be broken down into macronutrients and micronutrients. Macronutrients are going to be things like carbohydrates, lipids, proteins, and nucleic acids. Your micronutrients are going to be more of your different minerals and vitamins. Metabolites are going to be byproducts of metabolism. So metabolism is kind of in the word. These are also really important for your body. And both nutrients and metabolites can either be organic or inorganic. So inorganic compounds do not contain carbon and hydrogen as their primary elements. That is not to say that they don't have carbon and hydrogen in general, but organic compounds tend to have really long strands of carbons and hydrogens. You'll have more than one typically. So some examples of inorganic compounds: CO2, carbon dioxide, H2O, water, O2, oxygen molecules, and then many acids, bases, and salts are also considered your inorganic compounds. Your organic compounds are usually those long chains of carbons and hydrogens. Carbohydrates, lipids, proteins, your macros are all going to be considered organic compounds. So it's not as intuitive as you might think, because a lot of people tend to take organic compounds and think of them as things that are good for you. So you might have things like water in organic compounds. mistakenly, but just remember how they relate to carbon and hydrogen and decide from there whether they're organic or inorganic. So water. We're going to spend a little time talking about water because it is one of the most important molecules in our bodies, debatably the most important molecule in our bodies. It's going to make up 2/3 of your body's weight. Around there, might be a little less, might be a little more. Definitely depends on your consumption and your amount of fat and muscle in your body. Water acts as a universal solvent. It has some reactivity, a high heat capacity, and also has lubrication. So we'll talk about each of those properties. Okay, so water is a universal solvent. That's because many things tend to be water soluble. A solution is a mix of 2 or more substances. The solvent, in this case would be water, is the liquid that solutes dissolve in, and then solutes would be the dissolved substances. So let's give the example of salt water. The solute would be the salt, the solvent would be the water, and the solution would be the salt water. It only counts as a solution if the solute or the substance that you're putting in the solvent dissolves. We have other names for it if it doesn't dissolve, so we'll talk about that in a second. So in solutions that are considered to be aqueous, you'll know that water is the solvent. That's just what aqueous solutions mean. More substances dissolve in water than any other liquid, which is why it's considered the universal solvent. There are a lot of chemical reactions that take place in water or that use water as a reactant in both hydrolysis and dehydration synthesis reactions. So it tends to have a sort of reactivity generally because of that partial positive, partial negative charge that comes along with water. It also has a high heat capacity, so the definition of heat capacity is the quantity of heat that's required to raise the temperature of something by 1 degree Celsius. So if water has a high heat capacity, the temperature has to be high in order for it to boil. So in order for it to change from a liquid to a gas. So when water is boiling, it's changing from liquid water to water vapor. That's what that steam is coming off of it. Also, when liquid water turns into water vapor, there's a heat release. So as you're sweating, if you're exercising or outside when it's really warm, you have a heat release from that sweat. Part of it is due to the change from the liquid to the gas, and then part of it is due to the air current blowing over the sweat. Another property of water having this high heat capacity is that the freezing points and boiling points are far apart. Although, like we said earlier, all of the states of matter for water, whether it's ice, whether it's liquid water, whether it's water vapor, all occur at physiologically possible temperatures, which cannot be said for any other liquid. Thermal inertia is the idea of the temperature of this water changing slowly, or the temperature of anything, and how it changes. So with water, it helps to stabilize body temperatures, that it's able to have this flux of temperatures. And then it also provides lubrication, so there's not much friction between water molecules. And if water is introduced to a surface or between two surfaces, there tends to be less friction between them. So there are some implications with wet roads, you tend to hydroplane on wet roads because there's that water between your tires and between the road, causing less friction. There's also fluid in between joints and joint capsules, so it provides kind of a lubrication between bones so that they don't grind together. So we've said previously that water is a polar molecule, so it has that partial positive, partial negative charge on it. In aqueous solutions, inorganic compounds are going to undergo dissociation, where they split into smaller molecules. With ionization, that's a dissociation into ions. So in an example of salt water, when salt, NaCl, is introduced to water, once it dissolves, that NaCl is going to ionize, dissociate into sodium and chloride. They'll be separated. It's really important as a function because in the body this is really necessary for muscle contractions and for nerve functions, and we'll talk a lot about that as we go forward into our organ systems. So aqueous solutions that have cations and anions can actually conduct electrical currents, which is part of what makes it so essential for muscle contractions and nerve functions. We do have this electric current that runs through our bodies in specific ways, like for our heart contractions, for our nerve impulses. We have need for these cations and anions in a lot of our physiological processes. So here's a picture of water molecules and of sodium chloride when it enters water. So you see that sodium separates from chloride, so it ionizes or dissociates. Eventually, a lot of these organic molecules will dissolve, but they do not dissociate. Electrolytes are going to be our ions that are conducting that electrical current. So an example is NaCl. There are a lot of other electrolytes listed here below. Any changes in electrolytes in our body in concentration, they disturb all of our body's vital functions. It is really, really important to keep electrolytes up if you're losing them for some reason. So if you are exercising a lot and not replenishing your electrolytes, if you're really sick, vomiting, diarrhea, that's all depletion of electrolytes. If you don't have enough or you have too many molecules of potassium in your body, you can have heart arrhythmias. Too much or too little of calcium can cause muscle spasms, contraction, or even tetanus. So there are a lot of implications for some of these electrolytes if they're in too high or too low amounts. So it's extremely important to maintain your normal electrolyte levels if you're depleting them for some reason. So compounds can be either hydrophilic or hydrophobic in nature. So philic means liking or loving. Hydro means water. Phobic means fear of. So hydrophilic compounds tend to like water. Hydrophobic compounds tend to dislike water. So glucose is a hydrophilic compound because it can be in water, travel through water, dissolve in water completely fine. Hydrophobic compounds like cholesterol, which is a lipid, lipids, fats, oils tend to be hydrophobic. You can see this if you ever are cleaning a pan that has oil in it and the water and oil separate. That's because the oil is hydrophobic and does not want to dissolve in water or mix well with water. This has a lot of implications. We'll talk about this a lot when we come to tissues and we see, and even next week when we do cells, and we talk about how our cells have this lipid plasma membrane. So because we have this hydrophobic membrane surrounding our cells, we can keep things out. We can keep liquid out that we don't want to come into the cells, and we can keep the liquid in our cells from traveling out. So it's really important to maintain normal physiological function. So colloids are going to be solutions that contain dispersed proteins or large molecules. So things like Jello. Whereas suspensions are going to be where you see these large particles in solution. An example of a suspension would be sand and water. If you try to mix sand and water, the sand could be suspended in the water for a temporary amount of time, but it will eventually settle to the bottom. The same goes for whole blood. If you ever have a blood sample taken, initially it will all look like the blood is together and forming one color, but if you let it sit, the cells, which are heavier, tend to float to the bottom and separate from the liquid plasma portion of the blood. Okay, so this is where we'll pick up next week when we continue this chapter. Let me know if you have any questions, and good luck with the rest of your week.